Okay, guys, so welcome back. We're going to continue. We're really finished off the chapter 4 content. I had almost finished it off in the last video, but the video seemed to have been running long at that point, and so I cut it off maybe a little bit early before we finished off the chapter 4 stuff. It turns out, I think it was only like an hour and 5 minutes long once I got the editing down. So I probably could have waited a little bit longer, but whatever. We'll finish it off now. We'll finish chapter 4 off now. So where we left off was, I had gone through the example of the previous figure, right? This guy right here, figure 4.23, walking you through 5 iterations, as it says there in the summary at the bottom, of the learning real-time A-star algorithm, right? So got a very limited one-dimensional state space. We're just showing you how the agent could bounce around through the different states using a combination of step cost or action cost, path cost, and heuristic score, or right, a guess for how much it would cost to get from a state to the goal state, right? And so we were showing how the algorithm was updating those heuristic scores, those costs, as we were going along making decisions. And eventually that gets you, away from some global minimum or some global maximum to get you towards your goal, right? So I gave you an example of that last time. So what I wanted to do now to finish this off is just, give you the high level description, point things out for the algorithm, for the pseudocode from the text, just point things out, tie it back into the description that we had last time. And just remind you, make sure that you understand this, make sure that you understand, how to read the code and what everything means. And then you can imagine, how you might implement this in your favorite programming language. So I've added on Blackboard a copy of the Python implementation of this language from the publisher's repository. So you can check that out. And remember that you can go to their repository site and see versions of all these algorithms: Python, Java, C#, I think there's Lisp, and there might be 1 or 2 other languages there too, but I don't think that they have implementations of everything, right? So you can go see different examples of these things being implemented. But anyway, so let me summarize this algorithm for you again. So, what are the inputs rules? So what this is an implementation of the agent function for, the learning real-time A-star algorithm, right? So this would be controlling your agent, okay? And this is a type of learning agent because it's learning about the costs to go from, each individual state to get to the goal, right? That stuff's getting updated. And so it's remembering those costs and how they're changing. Okay, but anyway, so this function is mapping a percept identifying the current state that the agent's in. That's what the S naught is referring to, similar to the previous algorithm. And so it's mapping that percept onto an action, right? So there's no sequence of actions here. It's just, hey, what's this current percept that I have, indicating the type of state that I'm in, and what action should I take right now, right? It's a form of the Hillclimbing algorithm, as we talked about previously. Okay, so anyway, so your input, a percept, it's going to tell you what state the agent's currently in. So remember what the persistent stuff is, right? This is stuff that the function has access to that stays updated, right? It doesn't go away. They're not local variables. You can think of them as global variables or static variables, to use C++ or other language terms. So what do we have? We got result, which is a table that's indexed by state and action, starts off empty. Uppercase H here, that represents a table of those cost estimates, right? And so those are indexed by state, and that's empty initially too. So back in figure 4.23, these inside each of the nodes, the 2, the 4, the 3, those are the cost estimates. And so that table is keeping track of that, and each one of these nodes represents a state, and so you can access that cost estimate by using the state as the index or as the key, right? So that's what that's representing. And so S and A, as in the previous algorithm we looked at, this is the previous state in action, initially null, right? So you kind of keep track of where you were, okay, and you're getting a percept of where you are, and then you have a table that's keeping track of all of those cost estimates, and then you have a table that's keeping track of the results of actions, okay? So here's how it plays out. And remember that you're just making a function call to this thing to determine what type of action you should take given your perception of the state that you're currently in, right? All right, so anyway, you're trying to find a goal. So percept's passed, you then turn and pass that percept to your goal test function, right? So you're just asking the question, is the agent in its goal state? If it is, stop, done, it's over. No more actions. You've gotten to the place where you want the agent to be. Leave it alone, okay? Now, if that percept indicates that we've got a new state, or that the agent has transitioned into a new state, right? So that means that that state is not in this table of cost estimates, right? So that's why it says not in H there. Then what? Well, the then part, the second part of the if, right? This is saying we'll take that cost estimate, lowercase h is referring to the heuristic function that's going to give you a cost estimate of going from that state that we just perceived to the goal, right? So assign it to our table uppercase H, right? And so the S naught inside of the square brackets is serving as the index here. So this uppercase H, this is our table of all of those cost estimates. S naught is the key or the index accessing one of the elements of that table, and then we're assigning to that particular index, to that particular cell in the table, our cost estimate, okay? So if you're thinking dictionary in Python, you're thinking associative array or some type of associative array in other languages, right? So the key and the value are being associated to each other in this table, uppercase H. Okay, so what is this if part doing, right? What's this if statement going to be doing? So if S is not null, that means that if your previous state is not null, right? If you didn't just start, right? If the agent's already taken some kind of action, it's transitioned from some other state, right? Then what that means is that based off of our new percept, right? That's going to tell us about a new state. That new percept, it has to be added to our result table. So what that's doing is that's keeping a record. That's saying, well, look, here's the result of the state we were in and the action that we took. The result of that is going to be this percept S naught, indicating or identifying what our current state is. Okay. Now, once we have that, then this next line is saying, all right, let's go ahead and update our guess, right? So this is saying, and we'll see when we look at the LRTA star cost function here in a second, but this is basically saying, all right, what we need to do is we need to update that score, right? So you take a look at, say, the first iteration A here, right? The agent started off at 2, and then it decided that it needed to move right, and then after it moved right, then it had to update the node where it was at, right? The value, that heuristic value, measuring the distance from that node to the goal. And that's what this line right here is indicating that needs to happen, okay? So the cost function we'll talk about here in just a second, but A right here, there's an action B that is going to need to be taken by the agent for the state that we just perceived, okay, and that's going to have to minimize their cost, right? So what that's saying is take the action right now when you decide to move left or to move right. That's saying take the action that will get you the smallest cost, right? So in iteration A up here, that mean that action was go right, okay? And then once you've taken that action, then the current state that you just perceived, it becomes your previous state, okay? So then after you've updated your previous state, return the action that the agent should do, right? So in this case, for, like I said, iteration A, that action was going to be what? To go right. So then the agent would actually execute it. Okay. Now the cost function. Let's see here. So LRTA star cost. Remember, we were talking about how decisions are to be based off of the step cost. Right. Let me go back again. The cost to move to the right. So that's the one there, right? But also the cost of the estimate to get from the new node, right, the new state, to the goal. And so that's all this is right here. This is just encapsulating that in this function, right? If the current state is undefined, then go ahead and just return the cost of our previous state. That's what this is saying, because remember, this is you're trying to move from the previous state, that's what S was, taking that previous action, that's what A was, to the new state that you just perceived, right? And so if that new state you perceived, if that's undefined, if that's not possible, then just go ahead and return the cost for the old state you were in. Otherwise, right, return, this first part right here, the C function call, this is saying return the cost of moving from the old state based on the old action to the new state, plus, right, take a look in the table of cost estimates for that new state. So return, that's just saying return the cost of the 1 plus the 2, right? Because H of S would allow us to access the cost for this state right here. Let's say that this state was S, okay? All right, so I think that's everything that I want to talk to you about with this, right? So the big key pieces, just to summarize, hey, look, you got tables. You're keeping track of, what the estimated costs are for each state to get to the goal state. The function is mapping a percept for a state that the agent has moved to some action that it should take, and you're updating your cost estimates based off of every time you move, right? And you're trying to choose that action that is the most cost effective, okay? And you're making those choices, you're judging that cost, you're using a cost function that's taking into consideration just the plain old step cost, the cost to go from a state to a new state based off of some action, plus using that table that's remembering all of the estimates, an estimate to get from the new state to the goal state, okay? So the environment's being mapped by that result table, right? You're learning about right here, that result table, right here when it says result S of A, we're assigning S naught or percept to it. This right here is uncovering the environment, okay? So we're learning about that. We're updating the cost estimate for the state, right? Making a best guess, okay? And what's important here is that you assume that actions you haven't tried yet are going to get you to your goal, right? So by doing this, by making that assumption, it's kind of almost common sense, right? You're making sure that new paths aren't going to get unexplored, right? You're going to ensure that there's always going to be something that this agent is going to try. And so there's a term for this, for what this algorithm is doing for this idea, right, that some actions are eventually going to get us there. Because remember, you can't see ahead. You're not playing this out virtually, creating a big old search tree like we did with the chapter 3 algorithms. All you can do is take a look at your local neighborhood. It's a local searching algorithm, right? But anyway, so if you make that assumption, then hey, we're going to try all the different types of paths that we can. Anyway, so this is known as optimism under uncertainty. Okay, so a couple of last notes here, and then we'll summarize, and then we'll be finished with chapter 4 content. Right, you're going to find a goal. You're going to find your goal state, so long as if you're in a finite, this should say finite. You will always find a goal in any finite. That's a mistake. That should say finite, safely explorable environment, right? So long as the agent doesn't, or isn't in an environment where it can be destroyed, and the environment is fixed in size, it's not constantly growing, you will find a goal using this algorithm. You'll find your goal state. Okay, an infinite state space is not complete because the agent might be wandering away from the goal, or the goal could change, or your spaces could be so ginormous that you never actually make it back to your goal, right? And so, a little bit of big O here. If you have end states, in the worst case, you're going to explore that environment, you're going to find your goal, you're going to flesh everything out in big O of n squared. Okay, so let's see here. What else we want to say? Right. So these agents, when you're doing your learning, we looked at a couple of ways you can do learning where we're updating the estimates to find the goal from a particular state, but also backtracking, what your plan B was in the previous algorithm. You're going to be mapping the outcome of each state as the exploration goes on. That's what that result function was doing. You need to have in the LRTA star algorithm. Sorry, I had a brain fart there for a second. You need to have accurate guesses, those cost guesses for each state, because remember, that's part of what the algorithm's doing here, is it's keeping track of, as you move around, it's learning what the costs are going to be to get from one state to your goal, and to your goal state. And the more you explore, the more you poke around, the accurate those guesses get. Okay, so once you know these things, once you know about the state, your best choices are going to be made by what? You want to go to the lowest cost choice. So you're being driven by that cost function. Okay, so it's a form of optimal hill climbing, right? Because you are going to be moving uphill. Now you might have to backtrack a little bit. We saw that there's a little bit of whipsawing going on there, but it will get you to the goal eventually. Okay, now not the brightest agent, because it does do that whipsaw thing. It repeats visiting multiple states, at least it did in the example that we looked at, or it can do that. So future agents, future algorithms will find some ways to improve things and make our agent a bit more intelligent. Okay, so let me just summarize really quickly what chapter 4 was about. Right, so let's just go through this. Hill climbing. Right, so the other types of local search algorithms, you need to make sure that you have a complete state formulation. Right, so we talked about what that meant. We have to spell out, what is, what are these states going to look like? How are we going to move around? That sort of thing. The hill climbing algorithm, overall, fewer nodes in memory, right? Because you're only considering your current node, which represents the state that the agent is currently in, and neighboring states that the agent could move to, right? You don't have to have a frontier. You don't have to keep track of, you don't have to have this huge frontier like we had in the chapter 3 algorithms. You don't have to keep track of an explored set or anything like that, right? Fewer nodes in memory. Okay, now simulated annealing, it's a form of stochastic algorithm. Now remember what stochastic means. There's randomness in there. Okay, and we talked about how this thing worked. It was initially, your guesses were going to be way off, and then eventually you were going to start getting your guesses narrowed down closer and closer and closer. Your errors are going to get smaller and smaller and smaller and smaller. until you find a solution. So if you've given enough time to cool, and that's what that's referring to, right? You start moving away from your goal less and less and less. So you will find an optimal solution so long as you've been given enough time to cool, right? So this next bullet point here, delete all this, ignore it, because we skipped over a section that talked about linear programming and convex optimization problems and all that. So you can just skip over this bullet point, forget it even exists. Okay, we talked about genetic algorithms. They are a type of stochastic hill climbing search algorithm. They are stochastic. There is randomness there. You know, the randomness comes in the mutation function, right? When you put together a percentage based off of the fitness function and the overall population, right? That gives you a percentage chance for a particular individual in the population to be chosen, right? So there is randomness there. Okay, so these things, in addition to the randomness, large population, right? As you're coding this thing, you're going to find, I think, that the larger your population, the better results you get, more often than not. Okay, and this thing is driven by generating new states, multiple new states for each generation, and those things are generated by what? Again, that mutation function and a crossover function. Okay, so non-deterministic environments, right? So these guys have to have, when you're working within a non-deterministic environment, agents are going to have to use that and/or search, right? Why? Well, because you don't know the outcome of the action that you're going to take until after you've taken it, right? So the solutions took the form of what the text refers to as contingent plans to get to their goals, right? Partially observable environments, right? You don't know everything there is to know about the environment. You need to keep a belief state, right? A belief state. Because in partially observable environments, you could get the same percept from different states. So the agent has to keep, you know, track of what it believes, right, about the world. And that belief state represents what? A bunch of possible physical states that the agent could be in at any time. And through consecutive actions, you can narrow down, or the agent can narrow down, which physical state it actually is in. Okay. Let's see here. Percentilist problems, where you have agents that are completely and utterly blind, right? So standard search algorithms can still find a solution for you because you're not searching the physical space, right? That space of physical states, because you can't know for certain where you're at within the physical space all the time, right? So instead, you can search on your belief state, because the agent always knows, or you always know, what you believe about the world, right? So there's no uncertainty there, right? So exploration problem, that was the last couple of things we looked at towards the end of the chapter. Got an agent, doesn't know anything about the states, doesn't know anything about actions in its environment that it's operating in. The online search, right? That is a type of search where agents are building a map, right? They're learning about their environment, they're exploring it, and they can find that goal if it exists through that series of explorations. Okay, anyway, so that's going to be the end of chapter 4. So next up, we're going to take a look at chapter 5 and game playing. All right, so thanks for watching, and we'll see you in the next video.